Hello, everyone. Uh, I know that we have 2 minutes to stream, so no worries. We won't get started yet. I just wanted to come up here and say hi to all of you, answer some questions if you have. I see that people are already chatting about project and stuff like that. So, like before, let's see what's up with you guys and stuff like that. How you been? How's your week? Okay. Uh, no worries. You have until tomorrow midnight, and yeah. So I know that we are a bit of uh, um, like short time span. I know that you potentially all have studies and jobs and stuff like that. So I will have understanding if you are a bit late, but sorry I can't accept more than 24 hours late. Um, but yeah, just relax. Next week we won't have any homework. So today we are finishing the first part of the machine learning introduction. I would say like simple machine learning and stuff like that. And because next week we will jump into much more advanced content like deep learning and stuff like that, I will not give you any homework. So just relax. We won't have a guest lecture next week. So we'll have office hours, obviously. So if you have any like stuff that is unclear between uh, this part of the course and the next part, and the Friday we'll jump straight to deep learning and talk about neural networks and advanced algorithms that you potentially everyday use, like Google Translate, Google Search, ChatGPT, and stuff like that. But yeah, so today it's a bit of a more relaxed content. We are finishing with unsupervised learning. We have a small, um, I would say, notebook that we need to complete to go over unsupervised learning and stuff like that. Uh, yeah. So thank you so much for great comments about Marco's session. I by the way, it will be live on YouTube today or tomorrow. It really depends on the YouTube like processing. It takes some time, but yeah, it's already uploaded, so it's really depending on them now to how long it's going to be processed. But yeah, thank you so much. Yeah, and so, by the way, before we start, we have two options. So I just wanted to discuss with you to see like what speed of the course or the content that you like to have. So the option A is to go over unsupervised learning, that we are going to go either way today, and then jump to ML project lifecycle. So just speak about like all the things that you need to know and like care about, questions that you need to ask yourselves or your team members and stuff like that when you're working on a machine learning project. It's going to be really important. So whenever whatever machine learning project that you're going to do, those are basically points that you have like a checklist to ask yourself and your team. um, so option A is to cover all together today. Option B is to cover only unsupervised learning and to have just a short session, so about hour and a half. And then next week, instead of going to deep learning next week, we can prolong that and go a week after, so in 2 weeks, and the next week to have only for project life cycle. So all options are okay for me, just for you, like, okay, cool. So both today, amazing. Cool. So then let's get started. Okay, so we talked about so far about supervised learning. We talked about classification and about regression. Both projects um that you talked about, sorry, that you worked on, were in the regards of supervised learning. So Just to recap, supervised learning is a type of machine learning wherever you have a data set that has some labels connected to it. So you already know what you would like to achieve. Sometimes you don't know. You don't know what you would like to have, like in front of you. Sometimes you just want to give the algorithm your data set and say, hey, just figure it out what you want to have. And that's the case of unsupervised learning. So unsupervised learning is basically that, finding patterns. Finding patterns so you can do something with those patterns. That can be clustering, that can be like many other stuff as well. So such as dimensionality reduction. So, but in this case, we had a case like this. We have training set images, for example. So far, we didn't work with any images, but let's say you have an image of a number. Examples here are called from the MNES dataset. We are going to talk about that in a couple of weeks. And you have some label associated to it. Like you already know that whenever you see this image, you would like to have a 6 of it. And that's fine. That is basically, I would say, 80 to 90% of all machine learning projects that you're going to encounter in the wild. Those are going to be most expensive ones because labels are not cheap, and about 80% of every machine learning project you will dedicate to data processing, data collection, labeling, and stuff like that. But like sometimes you don't have the labels, so that's where you apply unsupervised learning. And you can see here that unsupervised learning, you're just providing set of images. You don't know that this is image of 6 and stuff like that. And you provide some kind of algorithm to it, and you find patterns and say, hey, this is pattern A, this is pattern B. Algorithm does not know that this is 6 or this is 7. Those concepts are really high level, and those high level concepts are for us humans. So whenever you take a look at this subset of images, you will understand that this subset is dedicated to 6s, but n is for 7s. But for computer itself, it just looks for plain numbers or statistics that you are providing to it, and that's basically it. So that's how unsupervised learning works. And you group them and so on. The cases of unsupervised learning, the one that we are going to talk about today is called clustering. So finding those groups of data together, like all images of 6s, 7s, and so on. Then you have dimensionality reduction. Maybe some of you heard of an algorithm called PCA, Principal Component Analysis, which basically takes your data set, and if you like to visualize it or make it more simple, you can take that algorithm, for example, and make like dimensions, make less of the dimensions. We won't cover how PCA works in this course. If you'd like, I have some amazing resources for that. We are on unsupervised learning. We're just going to talk about clustering because that's something that you're going to work most in practice. There is anomaly detection as one that can be solved with clustering as well. We'll cover that. But anomaly detection can be a case for itself. So basically having a certain pattern of data, and you want to see when something is out of normally like happening, like for example transaction in banks, then some monitoring for your models, like for example you can do anomaly detection on analytics as well. So whenever you have, like, let's say a peak of consumption in a certain device, you would like to understand why is that happening. Okay, we have a question. So how much do you think it would be have cost OpenAI to do the labeling and constant manual labeling correlation? Okay, so ChatGPT is trained. Okay, we'll talk about text in 3 weeks from now, but text can be trained without labels, and ChatGPT as itself is trained like primarily without labels, and then used reinforcement learning on top of it to finish the training and simulate the chat. So how that works is basically you have certain amount of words and you would like to predict the next word. So the next word in that sense is a kind of a label. So you know that you, for example, I have a, and then there is a certain small group of words that can go after that. Like you can say I have a going, like word does not go after I have a, for example. But you can say I have a table, car, I don't know, laptop or whatever. So noun is potentially going to be there. And like in text, when you're training those kinds of algorithms that we are going to train as well, you'd like to have certain amounts of words that as an input, and based on that word, you like to predict the next word. And ChatGPT, BERT, that's going to be released by Google. No, sorry, BERT, Bard and BERT. There is a BERT algorithm that we're going to use. Then Lambda and yeah, many others. Those are generative models. Generative models basically means that it's going to generate text based on probability. So you have a language model of English, for example, there is 160,000 words, plus minus, in English, unique words, and you would like to generate the next one based on a given input. And whenever you have those big models like 1.5 trillion numbers as they have, I think like it's some crazy number of parameters in ChatGPT. But basically, you have like huge amounts of data, and whenever you have those samples, you're basically providing more and more idea of what next word should be after you say this sequence. So if you have this sequence repeating, let's say 10 times in the data set, you are most likely to predict the next word correctly because you saw that sequence 10 times. Okay, so basically that's how you train. And now, like what they did on top of that, they already train it on crazy amounts of data, like books, Reddit, like websites and stuff like that. And then they used reinforcement learning. So, for example, you and I sit in front of our computers. ChatGPT generates, based on some questions, it generates like 5 different answers, and you and I sit in front of computers and select what what answer we find most correct or most appropriate for the question. And they paid 200 more people from Africa. If I remember correctly, I read some news article. I don't know if that is 100% correct, but they paid like really small amount of money per hour to those people to just sit in front of a computer to say what's right, what's wrong, in the sense of the answer. And that's basically how ChatGPT was trained. But generally, those language models are kind of a supervised learning, but not so directly labeled. Most of the real world project would be semi-supervised learning, right? Since I assume you have a raw data, but have a create your own label data set after doing unsupervised learning. Can you share any Okay, so that's a great question. Generally, semi-supervised learning is not that common. Like you will have semi-supervised learning, let's say in a Tesla car, in a self-driving car, where you label certain amounts of data, certain amounts of situation, but you can't like that's too big of a subset of scenarios that can happen in the real world to have all of those in your training set. So what they do basically, they train on a certain amount of those crazy situations and common situations, and they say if this next thing happens, replicate what human will do. And that's basically human in the loop training, where they either follow what driver does in those scenarios and having 8 cameras like following what he or she does, and that's creating additional data for them, and that's basically used to additionally train that model and stuff like that. So it's kind of a semi-supervised learning. Then we talked about Marco's talk here. So when I worked with Marco in Styria, so the first project where you upload an image and find similar images to that, they worked on a label dataset and paid a lot of money to label the dataset. But then we had some like problems of isolating object itself. Like you have a vase sitting on a table. You would like to have the vase only detected and not the table itself. So we had to use some semi-supervised learning techniques to isolate that object because we didn't have like that object circled and stuff like that. In the real world, you would basically take most cases and invest money or your time, depending on what you have, in labeling more data if that's required. We'll talk about that in the project like layout way. But yes, you would like to, whatever project you have, you would like to transfer it back to supervised learning, but because we research that the most, and those are like, I would say, easiest to solve. And let's say in photomat, where we trained the algorithm to predict like what's happening in, or like what mathematical formula is in the image, we labeled crazy amounts of data. We had about 20, 30 people constantly labeling more and more mathematical formulas and images just to extract what's on there. But to be like semi-supervised, it's amazing. You would use it sometimes, but generally, I in my experience, you would likely to fall back on classification whenever you can. That's basically how it works. But yeah, it's a great question. Thanks. Yeah, most data is not labeled, and that's correct. Like you, uh, so most projects, most companies that they consult are not ready to take on machine learning at all. Either they don't have data, or they have data, but it's not labeled. And that data, or sorry, not the data itself, but the task they would like to have is not optimized for unsupervised or semi-supervised learning. So either way, they would need to invest time or money or both to label the data. So whenever like that happens, they either like project for next couple of months to label the data, hire external or internal team to label that, and then we do machine learning project if needed. Like sometimes you don't really need machine learning. So we talked about that, and we'll talk and iterate that machine learning is an amazing solution, but not always. And yeah, so to reference to the Tobias talk, most data is not definitely labeled. And if it's not labeled, that does not mean that it's useful for unsupervised learning. It just means it's not labeled. So that's it. Sometimes you just need to crunch down and label it. Yeah, cool. So to give you a bit more of a tangible sense of what clustering can help you with, basically customer segmentation in marketing. We will do that exactly today. So I actually worked with one company that they didn't have any clear segments of market that they wanted to target, and basically they needed some case of sampling their audience and basically creating targeted marketing campaigns based on the parameters. So we done that, and they actually done marketing campaigns pretty successfully after that. Then there are cases, for example, in law firms where they are starting digitalization process, and that's really tedious process because like when you have old company that like real estate company or a law firm that has all documents like not scanned or digitalized or whatever, and they suddenly start digital transformation, and one of those processes basically scanning a bunch of documents or typing them out. And whenever you have those cases, they are basically just dumped in some folders online, and that's basically it. And like, to be honest, that's much better than having them stored in some archive where it's not searchable, but that's not useful as well. So one law company here in my country basically used clustering to group the documents together, and they found out that they can do that pretty well. So they basically ended up having like traditional cases versus corporate cases together, and then inside of them, like specifics of contracts, like all the other documents for like they had about 30 different clusters. I'm not in the law, so I can't tell you the names of those clusters, but generally what they did is basically one of those were plain contracts. And then you can do basically image segmentation that we are going to talk about and do image segmentation in the last week of this course. Generally, you're basically clustering pixels of an image together automatically with deep neural networks. So you're not going to do that manually. No worries on that. But yeah, there is a case of clustering certain parts of images together to find out the objects. We have some comments. So best option, opinion, sorry. Option. IG to reduce labeling cost is outsourcing it to countries like India, Africa. I don't know if that's economically correct. I don't know if it's morally correct. That's debatable, and I don't really. I'm not in a good position to debate that. But if you like straight look for from the standpoint of cost efficiency, yeah, my opinion is if I were to build a labeling team, I would take different subsets or groups of people. So I would take definitely people from Africa, from India, from Asia, like some country in Asia, from Europe, from US. Like I'll try to get as diverse population of laborers as possible, pay them equally, like no matter the country. Equally low or equally high, that's debatable. I don't want to go into pricing right now, but just to explain you my thought process. So basically I would create a labeling team as diverse as possible, have different genders there, different religion and different stuff like that, and then put them to label certain topic. It does not have to be in those like to encounter for religion stuff like that. They can label only cats and dogs. That's it. Like it does not have to be a complex task to label. I'm just speaking about difference in labeling, because right now when labeling people labeling the data set, they're generally like there are biases pre-built in those areas. You will have biases in Africa as well as in Europe, as in like first world countries, anywhere, and every bias is like specific to that region. And if you had a lot of those areas targeted, and there are techniques to overcome like biases by default, but if you have diverse set of labelers, you are theoretically decreasing the bias. I'm not saying that you will 100% decrease the bias, but in this sense you would ideally not have those types of biases in your data set. Like we can recognize actually in ChatGPT that even though they hired most people from Africa, they still have bias. And it does not mean that's wrong. It's just, it is what it is. Because like those people live their lives, they see only one side of picture and stuff like that. So basically that's what's naturally going to diverge from the labeling people. And that's fine. Like whenever I label my data set, I enter my biases so much. But yeah. Okay. So application of dimensionality reduction. There are some times of like, for example, need of visualizing the data set. Let's say you have a clustering data set. We are going to talk about them today. You'd like to visualize it. We won't go into that area today, but generally you have, let's say, 100 features about a certain person, and you'd like to know if you cluster them seemingly correct with your clustering algorithm, so you can basically decrease it to 2D or 3D dimensions, so you can actually use traditional visualization techniques to visualize them. And that's basically one. The other one is feature selection. So you can use features, basically dimensionality reduction algorithms to reduce the obviously dimensions of your data set to find which features are preserved, or the information from each feature is the preserved one, to capture what's actually important in your data set. And obviously compressing for storage and transmission of the data, it's generally not done. Because we have so much space right now to work with, either offline or on cloud, and like it's cheap. So people are generally not doing this, because any technique that we can mention here has its own noise entered to data, and it's not 100% reliable in the sense of restoring the data. So in theory, you could compress the data pretty well, much better than zip or RAR algorithms that does, but those are reversible, so you can actually get your data. From this, you will get the data with noise. So yeah. And then anomaly detection. So we talked about that as a part of unsupervised learning stack. So obviously fraud detection, let's say you have credit card transactions, you would like to detect those and see whether a certain transaction is a fraudulent one or not. You can identify defect items in manufacturing. So basically that's done all over the world using either machine learning or just some traditional techniques, but generally you would like to see automatically whether or not a certain piece produced is malfunction or not. And obviously monitoring systems for unusual behavior. So that's basically your traditional antiviruses that you have installed on computers. So they can use machine learning, or they can use rule-based algorithms that just determine whether or not some action or some type of file that you are downloading might contain some information or virus or whatever. Okay. So what is clustering? We talked about that, but generally you have a lot of data. You would like to find patterns in the data and group those patterns together close enough in a sense of space. So given a set of objects, so those objects might be images, users, whatever the data that you currently have, and you find basically structure in the data. So that's basically what it does. And as we talked about examples, we have customer profiling and advertisements. So for example, you can find actually what type of ads might work to certain people and test actually that instead of using A/B testing, for example. So how does clustering work? Basically, it's an optimization problem. You have certain type of data and you would like to optimize parts of parts of that towards the data set and find what actually works inside the data set and what are the patterns. Generally, like there is a loss. I said here that there is not, but there is kind of a loss, but you are not comparing that to some labels because you don't have them. So you're directly working with data itself. And if you remember the first algorithm that we talked about in this course, it was KNN. And that's basically that type of learning. So you have a data, you would like to learn something from the data. In KNN space, it was supervised learning. Now we are going to introduce something called K-means algorithm that we'll cover in this session as well. So two concepts to research here are variability and dissimilarity. So variability in data sets, or how variable or different certain parts of data sets are, and those can be captured using that algorithm. And the similarity is basically explaining like how different certain groups that we talked about are. Okay. So we can talk about these concepts in more details like here, or to save more time, I would suggest you read through these examples by yourself. Because we have to cover a lot more about projects themselves. But for today's session, we don't need to understand these concepts yet. Okay. So, constraints in clustering, just to understand what we are working with. There are different there are different methods and explanations that you can use, like for example silhouette value or elbow method. We're going to talk about elbow method extensively in this today, and how to determine did you find a good patterns in the data set or not. And like for example, there is a business logic that needs to be applied to the problem. So for example, we can't handle more than 5 separate marketing campaigns, and we talked about one of applications of clustering might be finding the best campaign there. And if you can test like 10 different campaigns, that's fine, but we can't actually put out more than 5. So you're just testing 5 as a 5 clusters and actually targeting 5 different audiences. And that can be and that should be directly transferred to that as well. And before we jump to k-means algorithm, we have to pre-process and actually work with the data set. So we'll jump to the data now, and then go back to the slides once we reach the point where we need to apply this algorithm. This file and the data set is actually linked to your to our Notion page, so you can go check it out and download it for if you like to follow along. And there is a question. Okay, so yeah, recently somebody read that there is much better a way of understanding what is the number of clusters than the elbow method. That's absolutely correct. One is silhouette number, silhouette graph. But yeah, you can watch actually. Oh, what is the name? I forgot it as well. But silhouette is actually one much better way to determining the amount of the cluster. But if you remember, please link it here. I definitely like to read about it. Okay, cool. So somebody mentioned Bayesian information criterion. I read about it. I never applied it myself. It might be a much better one. Yeah. Let me zoom into content, not to have the problem with. Nice. Thank you so much for putting the link. I will definitely open the link now and just remember it so I can put it in the Discord. Amazing. Yeah, I looked some. Okay, so let me just put it here for people to see what I'm actually looking. I'm checking out the link that our friend just posted. So this is the LinkedIn post about it. But yeah, so elbow method that we are going to use will take into account different set or different number of clusters that we tackle, and actually use that to find what is the difference between clusters. Right here, the big method, that Bayesian one, works much better. Like in this sense, it says that for based on elbow method, the 6 is the optimal one, but here it's 25, and yeah, by far we can see that here is much better one. But yeah, amazing. I'll definitely take a look at and read about this. Thanks so much. Great. Okay, cool. So the data set that we all have can be found in the link. Like for example, here we have this customer data. So I'm going to download it. And yeah, so basically that you can download this file as well if you would like to follow along. here. Okay, so to upload it, I'll need to bring it here. Okay. Okay. Great. So we'll use only for now NumPy, pandas, and matplotlib. And once we reach the point where we need to use actually k-means, we'll import that from our from sklearn. So data, you can name it as whatever you like. So pd.readcsv of customers data. Okay. So let me visualize it, what we currently have here. Oops, I missed the bracket. Okay. So we have 5 columns. Customer ID, which we don't really need. Here is mistyped, so it should be gender. So whenever you reference this column, make sure that it's referenced by this wrong one. You can rename it if you'd like, but here it's without D. Okay, so we have age, annual income in thousands of dollars, and then we have a spending score. We don't have any label here that we are looking for. By the way, you can always take a look and, for example, take these 3 features and predict spending score. That can be done. It's a regression one, but we are not doing that. We are taking all 4 and making sure that they are clustered together, so we can either focus the marketing efforts to it or whatever. Okay, so the first step is just to check whether or not we have the missed labels, missed data or nulls, and we have that. We've done that multiple times so far, so we're going to do it like this. And as you can see, we have all data filled in, which is generally not the case in real life, but that's something that we have here. And just to understand the data itself, we have customer ID, which we're going to remove because we don't need it. These are all in integers, and then we have the object one, which is a gender one, that we need to convert or keep it as it is, depending whether or not we like to use it or not. Okay, cool. So the first step for data pre-processing is to remove the column. So we can say new data is equal to data dot drop, and then customer, you can just copy it from here, customer ID. Oops, we have so many spaces. Okay, and then X is 1. So this will create a new data frame. You can visualize it here. Just make sure that we have all the rest of the columns that we actually need for this one. And yeah, that's it. The next step is for us to encode the gender column, and basically we can rename it at this point. So we can say new data of gender, or you can basically use gender and then and then drop the column with the wrong name. So whatever works for you, you can follow along in that sense. So I'll just keep it as with a typo. One last step for pre-processing. So I'll use another technique. So far we used, if you remember, dummy variables, but now we'll for first time use NumPy in that sense. So there is a function called mpwhere. And if you take a look at parameters, the first step is it will take a condition. So basically compare an array with a certain value, for example, that we are going to do. And then you will put what's the case when it's returning the correct one and what the case when it returns false. So if you check it out, basically here are the parameters, and returns the parameter with a 0 or 1, or basically the condition that we want to set. So here we are typing new data of column gender and equal to male. Oops. Male. And whenever that's correct, we'll put it 1. And when it's false, or where the value is for females, we'll go for 0. And let's encode it. And here show the data. So you can see basically that we coded that to 0 and 1. Okay, cool. So at this point, we have our data set. At this stage, if you were to apply your like supervised learning algorithm, you would need to select certain parts of data for training and another one for testing or validation sets, and then apply that or train the algorithm to the training set and obviously test it on test set. We don't have to do it here because we are actually taking all the users from our database and clustering them, putting them together. Whenever a new user comes, it will be in some of the clusters, it can be in the new one. So it's always going to take only data into consideration. Okay, but before we start with our k-means, let's take a look how actually k-means works. Okay, so the k-means is a general purpose clustering algorithm. That's the first step. And it's basically takes a centroid or a point in a space and determines where that centroid should be based on data. If it doesn't make sense right now, no worries. It will in 2 minutes. We take k as we did in KNN, and we define how many clusters we supposed to have in that data set. So we are by hand picking the number of clusters. And you can see already here that that's basically one negative side. Negative side of k-means clustering is we need to set up how many clusters we have to have in the data set. So we should know the data set much better than we know right now, for example. And it is very fast, but basically it takes a lot of data. It loads all the data in the space or in memory, and that's another negative side of it. Okay, so let's say we have this data set. It's any data set that you can imagine, and clearly we have here 2 clusters. We determine that by visualizing it. We don't know what each of these represent, and obviously sometimes if you have huge amount of dimensions, you can't visualize it. There is, as I said, dimensionality reduction technique, but for now, let's say we just visualize it as it is. We start by defining k, or how many clusters we expect it to have, and we initialize centroids. The initialization of centroids is random. So it takes anywhere in a data set and place those in the coordinating system. So it can be here, here, anywhere. That's one point. Another one, it takes any data point in a data set and put that data point as the initial coordinates of a centroid. So either random or some data point copied as a centroid starting point. Just remember this is a starting point. So I just explained it how it works. So basically those 2 are initially placed. Does not mean anything, but yeah, so it's randomly placed, and then basically starting from iterating there, or there is this forgery method where we are taking random points from the data set and using their their value for initial placement of those centroids. And now what we do, we take basically, this is not classification, this is just a line for representation, so this does not actually happen in the training time. But basically what we do, we take those centroids and compare the distance to each of the centroids from every single point in our data set. Okay? What this does, for each of the points, for each of centroids, you will have like distance to each of the points. Some points will be closer to this one, some points to this one. And we'll take and say, okay, these points are closest to the centroids A and these ones to centroids B. Okay? And that's basically how it's done. Now that we do that, we take a mean value of all points that were closest to each of the centroids. And though that mean value is the new position of the centroids. Okay? So that's basically that's how they moved it here. So just remember, so this one was placed here because it took all of this. And you can see some outliers in here that pushed this one to be more up. And that's how it ended up right here. Now that you do that, we see, is the iteration done? So for example, when we do the basic step and compute the distance and say, okay, does the new position actually differ from the current one? And we say it does, it differs, then we are not done. So we basically go and assign to nearest centroids. And that's basically what is done here. So we take, again, recalculate the new positions, place them here. So they are moved to the closest point, the average of all the points. We check again. Did they change the position from the previous one? And the obvious answer is yes, because they were here and now they are here. So we say, okay, cool. So let's do it again. We calculate everything again, recalculate the positions, and then check, are they changed? The answer obviously yes. But it's not changed by much. Okay, cool. So this is interesting point, and then we are done. And we determine the positions. So these centroids changed can be calculated in different ways. First one, you can set how many times are you going to check, and it does not care if your centroids are changed or not. It's basically doing that for as many times as you set. Or there is another one that you can say some lambda parameters, for example, and set it to a really small number and say, if the positions from the previous one to the new one is not that difference, like less than lambda, that's it. We are done. But that takes more time, obviously, but it's more correct. And on that point, we have a question. Is it guaranteed that k-means converges to a solution? Depends on the way that you're calculating the positions. So if you're setting amount of the amount of iterations, so let's say 300, it basically differs. You see it can be done in 200, but it can be 500, 600, 700 steps or even more. And if that's the case, in 300, it's not even close to converging. But if you set like small amount of change, let's say lambda that is 0.0001, and if the positions of centroids are there and not changing the positions by that much, you're converging. So if you're following that step, yes, you are about to converge. Now the question is to what? So here we were lucky that we guessed 2 for amount of k, for amount of clusters. But sometimes you would set 2 clusters, but actually there might be 10. And to your question, yeah, it will converge to something. What is the best solution for 2 clusters? But that does not mean that you are actually prone to have only 2 clusters. You should be having more. So that's something that is a problematic with k-means, because sometimes you don't really know what is the right amount of clusters. There are techniques such as we discovered, Bayesian one, and the silhouette one, and obviously one for uh, elbow method. So yeah, there are techniques to do that. Once you're getting the right amount of clusters, you're about to converge. Yeah, great. So there here for you are just some pros and cons of using k-means. So obviously it's very fast. We scale well. So whenever you have more data or more clusters, it will just optimize that for that amount of clusters. New points can be assigned to a new model, which is the closest one to the centroid. It's a general purpose one, and obviously easy to understand, which we did because like in 2 minutes. But we saw in second iteration that the position of one of those centroids were pushed back because of those outliers, and that's intentional like representation, because it is really sensitive to outliers. Sometimes you will have a couple of outliers in your data set that might screw up the algorithm completely and create additional cluster just for outliers, and you are about to do some decisions based on them, but they are basically black swans in your data set. We already discussed this disadvantage. We should know the amount of clusters that we're going to use. Obviously, limited cluster shapes. All cluster must be spherical with same radius. So that's one issue here. If we take a geometric one, basically you're going to converge in that like sphere-based shape because of the nature of the distance function that we are using. And result and performance depends on the randomness, random start of points. So obviously, like let's say you start your centroids randomly all the time, you would converge to the same solution per se, but like name of cluster might differ. Let's say in one iteration your cluster 1 will be cluster 1, but that same cluster in, let's say, after 3 iterations will be named cluster 3, just because randomly pointed centroid was there. That's it. And generally you would have clusters of the same sizes. It's not a rule, like I had seen like really different scenarios here, but like if you know that you're looking for 5 clusters, amazing. If you know that there are a couple of outliers, clean them. If you don't have outliers, even better. If you are okay with geometrical functions of this, great, use k-means. If you can converge to this, solve some of these problems and then use k-means, even better, because like k-means is, as I said, easy to understand, and it's explainable to your users. So whenever you use k-means, you know why decision was made. Okay. So that's basically it. We can continue with our code. So the first step here is to import from sklearn cluster, import k-means, and then we are going to define it with km is equal to k-means, and then if you remember our hyperparameters. So we are going to set, I name it calf, you can name it cam. Okay, and here km.fit, and just provide your new data. It's going to train it, and basically to find out what is the inertia or what is the difference between clusters, that's how much. Okay, this is great, but you know, we just use 3 because you trust me. You don't know why I use 3. We just use it. Obviously 3 is not the right answer. We just use it randomly to start with something. Now we need to optimize that to find optimal number. Okay, so I'll target that question basically. Okay, so inertia. Let me explain now before we go further. Um, Inertia is the distance, the average distance between each centroid and uh, centroid, and each centroid and the point in that cluster. So you're basically between cluster distance of each point to that centroid, and this should be equal or close to equal between clusters. Because you're, as we discussed, the pros and cons of k-means, you're almost always going to reach the same amount of data. But generally, yes, this is the basically distance between each point of that cluster and the center of that cluster. When we start now, we are going to start using and implementing our elbow method. Idea is to decrease the inertia because like distance will be smaller, more points will be to different clusters, assigned to the different clusters. That's basically what we're going to minimize now. Does that make sense? Okay, cool. So now that we know that, let's basically implement it. And you can name this list as whatever you like. So you can name it in cluster distance, for example. That's really explainable. And then we are defining k, which is in a range, equal to range between 1 and 11. Come on, 11. And just to show you what is actually this, you can actually like put it in a list just to create different set of cluster numbers. And now we are going to use this each of these to train k-means on top of it, and actually test which has the lowest or the optimal inertia. We'll make a decision based on elbow method right in a second. So what I'm going to do, I'm going to say for k in k, then I'm going to define km is equal to k-means, and that number of clusters is going to be k. Okay, oops, k like this. And then we are going to fit it to our new data. And then finally, in cluster distance, append km.inertia. Okay, so what we done here, we basically train the algorithm on multiple sets of k's and basically got what is the different in between cluster distances. But now logically, because we have more clusters, there will be less data in each cluster, so these numbers inertia will be lower. So obviously it's going to decrease if we add more k's. The idea of elbow method is not to use the lowest one because we can always increase it. And if I take, let's say, in the range of 1 to 24, it's going to be even lower. That's not the idea. The idea of this is basically to decide when the difference between inertia becomes that small that we don't have to increase the number of clusters even more. So for example, here between these two, it's pretty large, but here as well, like about 20,000. Here it becomes much smaller, so it's only 7,000. here as well 7,000, 4,000, so on. So I would argue that 5 or 6 is optimal number of clusters, and we are going to use them. Okay, just for your we can play with this, by the way, in different sense. Let me show you this. So KM test, you don't have to do it. I'm going to use k-means, but for number of clusters, I'm going to use len of new data. So I'm going to have as many clusters as data points in our data set. And if I train this on new data, and then it's going to take, okay, cool, and then check inertia, okay, it's going to be 0, because each point is going to be basically the cluster. So you don't have between cluster, sorry, the distance inside the cluster itself, because each point is going to be different clusters itself. So, okay, obviously you're not going to do this, but just so you know, if you take exact number of clusters to the length of data, you're going to have this. So inertia is going to be 0. Okay, so you can see basically that's the point where you will stop decreasing the inertia. Okay, so this was just an example to understand it, what's going on. Okay, so I'm going to copy my visualization code, just not to type it here, and instead of this, I'm going to name it like this. This was my working code when I made the lesson. Okay, so you can see basically how smooth this becomes. So basically here, the distance is not that large. So you can see here for number of Ks of 4 and 5, still a bit of a difference, but between here, like you can see, like that's already decreased. And here it becomes the difference between using 6 or 8 clusters is really small in comparisons to the before. So we can say, okay, for this data set, we can use either 6 or 5. So you can experiment with both. Let's, for this case, use 6 and basically go with that. So now that we have our optimal number of clusters, we can go and define a new called k-means. And then for number of clusters, we're going to define 6. Then we're going to train it. And that's basically it. That's now you have your trained algorithm and you can apply it. We can make some predictions. So predictions is going to define basically the number of cluster where each point lays. So you can call kmnew.predict and provide new data. And if I visualize it preds, I'm going to have 0 to 5 numbers, which basically means the ID of cluster that we're going to use. Okay, so that's basically it. Okay, so far you saw that we have cases where we need to apply a certain type of algorithms for clustering in this sense, and we found a way and experimented with the simplest one technique to find the optimal number of clusters called elbow method, where you basically take test the algorithm, train the algorithm on different sets of parameters, in this case number of clusters, and check what is the point where the difference between using 6 or 8 becomes like, you know, not so important. So you can just say, okay, this is the point where, that's why it's called elbow method, basically where it's big slope in decreasing the size of the difference between clusters, and then at one point we'll start to converge and say, okay, now it becomes more smooth, so we can start, and this is the point, this is the breaking point of optimal number of clusters. There is a question, I will target that question just in a second. Just so you know, there is another type of clustering that I definitely suggest learning about, which is called hierarchical clustering, where basically, for example, mean shift algorithm is there, where you don't have to specify amount of data. Okay, so just to plastically explain how that works, there are many different algorithms in that group, but basically we'll start by using each point in a data set as a cluster, and then expand it, like add more and more cluster to it. So you're basically expanding the number of points in each cluster at one point where you say, okay, I don't have more points to dedicate to that particular cluster, I convert. And that's in a really, really high level, short way, explaining how, for example, finding amount of cluster without specifying any k number. So for those applications, you don't have to know beforehand how many clusters are you going to use. Okay, so questions. So for your digit example, 0 to 9, we would go for k equal to 10 a prior, right? Yeah, exactly. In the hope that it can differentiate these 10 possible numbers. Yeah. Yeah, that's a good example. So this moment we'll pass to 1 hour. If you have any questions before we go to a break, we'll have about 4 or 5 minutes break, and we'll jumping straight to project lifecycle in the machine learning. But if you have any questions beforehand, shoot. Otherwise, let's go to the break. Okay. Cool. So let's go back. Let's make a break of 4 or 5 minutes, and we are back to the next section. Cool. Hope you are a bit refreshed, so we can continue with really interesting part of today's session. Okay. So obviously, if you have any questions now, I hope for this part to have as many questions as possible, because this is something that's going to be really helpful whenever you start working either with machine learning engineers or as a machine learning engineer. You can work as a business leader, you can work as an engineer, as I said, whatever is fine with you. And whatever is your role, I think you will find some benefits with the next session, with the next part of the session. So we are talking now about machine learning project lifecycle. I called it like that, but the agenda of this part is basically first data collection, then feature engineering, model training, model evaluation, model deployment, and monitoring. So we'll start from the first part, where we already discussed a couple of questions at the beginning of today's session about data collection, about data first approach. Then we are going to switch a gear and again speak with data, but in a bit different angle from feature engineering standpoint, and find our way into model area of the project. Cool. Obviously, as I said, I would like to know your experiences, if you have experiences so far. I like to know your questions. Like if you have any questions, just shoot. We'll going to discuss them as well. So starting with the first machine learning project lifecycle. By the way, slides will be shared with you, so no worries on that. And for each of the image, you have the reference where I took it. So some of the images obviously are not mine, and I just wanted to share that you will find links to those images in the description of the slides. Cool. So every machine learning project starts with some initiative, business initiative, business goal that you'd like to achieve. Like it can be simple as increasing the revenue, increasing the number of like visits to our website. Like there for example, for e-commerce, obviously you would like to increase revenue, but what actually leads to revenue is more visits, and what leads to more visits, it does not have to be a number of unique visits. It can be actually the length of a single visit. So how many items per session you're looking at? Like one client wanted to increase that. So obviously recommendation might be a good answer to that question, not the best one, maybe best depending on the project, but you're always starting with something that you like to achieve. That in that sense is a goal, like from the business side. You here can, as a consultant, if you're working as a consultant, you are going to help them research this point. But obviously, if you're an engineer, you're going to be given this. And that's where machine learning engineering starts your part. So first step, you get that and say, okay, cool. Let me get data. Do you have data? Some businesses do have data, but it's not labeled. We're talking about labels. And if they, for example, want to, let's say, filter out not safe for work content on the blog. That was one of the projects that I worked for, one blog. Like when you register, you can provide your image as a like icon, and there were really bad images there, and they needed an algorithm that will detect not safe for work content versus safe for work content. And obviously they did not have the data labeled. So one part of the project was for us to label the data, because they didn't have resources to actually hire additional team. And at the moment, they didn't have good candidate for a vendor of data labeling systems. So we ended up labeling ourselves. But that was fine, because like most people were banned manually. So we kind of looked in those banned cases. Are they banned for a reason of like using those images, or banned for a reason of providing some answers that were not okay and somebody flagged them? So we had a starting point. Obviously, those that are not in those brackets, we had to explore ourselves. After that, you're going to go and do feature engineering. Feature engineering is extracting useful information or creating more useful information from the data. If you remember our regression case, we had a case of predicting salaries, but our linear regression was not okay to solve that problem, so we need to add more features to it. So one of those cases were polynomial features, where basically we use that to add like squared and cubed features. So we created our polynomial case. That is one part of feature engineering. So creating new features, exploring the current ones, processing it in the sense of creating good inputs for our model. Then you would take that and do basically model training. Model training, we've done it multiple times. Obviously, in deep learning, it will be more code around it, but generally it's model time. After that, we need to evaluate how good that model performs. So we'll take like either all the techniques that we already established, like mean square error, if it's a regression, or mean absolute error, or R2 score, or whatever. Or you can, in the sense of accuracy, go and explore for binary classification, like obviously recall, precision, F1 score, and so on, or just pure accuracy. Okay. At this stage, you have the points of going back. So you say, okay, model evaluation proves that we are not okay, so we need to circle back and either invest more time to feature engineering, or actually we can't learn anything from data, so that might be an indication that we need more data, or the labels were incorrect. That happens as well. So you're going back even further in the pipeline and actually doing the data collection step again, or data labeling step again. If you circle this for multiple times and you actually notice that there is no change, you can go back to business and say, hey, the case that you are actually trying to achieve here might not be feasible using machine learning. So you can either change the goal, not you, the business, but that's rarely happening, or you can change the approach. Generally, that's not the case. It's rarely the case. It's always going to be around the data or the selection of the model itself. So you might go and change the different model and use a different model and use it all over again. After you've done this for quite a long time, you're basically done. At this stage, you have the model. Well, not quite. You need to use it somehow. Now you are done in a vacuum. You're done in your room, in your office. But now that model needs to be seen by some users. And that's where the challenging part starts. It's called here in this visualization DevOps, but there is a new region or type of engineering called MLOps, or machine learning operations, where people in those roles know the DevOps practices as well as the machine learning ones. So you take the checkpoint or the saved model and put that to certain infrastructure that can be actually integrated into bigger part of tool, and actually using that by users. So that's basically model deployment. So you are basically either exporting it, exposing it via API, or directly via backend, in the backend. So it can be directly, or a microservice, or it can be called offline as a part of a script, whatever works for your business. Like, for example, right now I'm working with one client. They're building a tool that they don't want to have model integrated directly. So they will call that model manually from their home computer. And that's fine. Like, that's how I'm going to quote unquote deploy that model to them, because that's what their business requires. You don't have to overthink the model deployment if actually something that client needs is really simple. Then you are going to serve that model, obviously interacting with that and basically exposing it. So this is all model serving or model deployment. Here are two stages. Generally, it can be a one-stage process, basically the goal of this stage will be taking that checkpoint and exposing it to like other parts of application. Then your model, when a model is deployed, you're not done. You're never done. You need to monitor that model constantly. So, what are the predictions? Did they have some change in statistics or the distribution or whatever? So that's where we start and saying, okay, is this prediction okay? Is this something that we like to change in potential and so on? And together with model maintenance, you are basically feeding information from model monitoring to model maintenance. What I mean by that, sometimes you'll notice that so many consecutive predictions were kind of incorrect. How do you know if new prediction is incorrect? Well, you can manually check. You can see how user reacts to it and stuff like that. And basically that moment you can detect data drift, model drift, distribution drift, model scaling, stuff like that, and basically use that to maintain the model. So what I mean by maintaining, it means that sometimes users are changed. Let's say you have a recommendation system, you're training it on data, and suddenly COVID struck. All your predictions were wrong because the pattern and behavior of your users are changed. The circumstances of those users are changed. So you need to take that into consideration and do the model over again. So now you're back at the square one and you do the process again. You collect more data if needed, relabel something if needed, and do every single step. Once you're done, you already have this provided for you in this stage. So you're just changing the checkpoint. So you're not doing everything from scratch, but generally that's how it circles. So the first step is collection data. So here are some questions to ask you when one, for example, somebody asks, can you... so before I continue, I have an interesting question. Time duration. Okay. It really depends. I can't like estimate it because from each like step for each project it will be different. Like I had a project that I worked for the really big client where these two squares, like data collection and feature engineering, took 8 months. 8 months full time, 2 engineers. Obviously, full team was 3 engineers, but 2 engineers, these 8 months. The model training was, model training was, if I remember correctly, 2 to 3 months. Model evaluation is collected to this. So these two are like happening together. So there is a lot in how to automate these processes, how to do like training and evaluation in the same step, doing tools like using tools such as MLflow or weights and biases or clear ML, stuff like that. So you're basically creating experiments, different hyperparameters, different models, architecture and stuff like that, and evaluating constantly against certain domain, certain test set or stuff like that. So basically in that stage, this took about 2 to 3 months. Model deployment model serving took really 2 weeks because, like, as I said, 3 engineers. So we had an engineer, like we basically done everything basically that project. But we had this part prepared. So whenever we completed this part, we were ready to deploy it. But yeah, and model monitoring as well. So yeah, basically that. And that project started 2018. We were done, or 2017. We were done by 2018, so about a year. And at that moment, we explained and taught their engineers on how to maintain the model. So that algorithm is still in production, but obviously there were quite a lot of changes. Right now, I mentioned one client that they want to have this offline on their computer. The whole project will take 2 months to complete. So everything, because they have already data labeled and collected. So I jumped on a call with them a couple of months ago and said, okay, do you want this? Like they find the goal, say, yes, we want this, we need this. I said, amazing. Do you have data? No. How to collect the data? I explained. And they sat down and explained to their employees how to collect data, how to label it and stuff like that. So I already have the data labeled whenever I jumped on the project. So this part is done by them. Feature engineering is done by me. So all these 3 blocks will take months and a half, 2 months tops. And then this will basically be really simple because obviously it's creating a Python script. So yeah, model monitoring in that sense is but a bit harder because it's offline model, it's not online. So that's going to be a difficult one. And the model maintenance will be done by me every month. So whenever they take more data, I will prepare it, retrain the model and stuff like that. But yeah, and that's basically how it. That's an example. Like in a Photomat Marco's example, like when they hired me to do that project, we had to do all of these in 3 months. So we done that on a 3-month scale, and I led that project to create that OCR model for mathematical formulas. Everything took 3 months, but we had about 25, 26 people across all teams working on this full time. So you basically have a lot of people working and you need to manage them correctly so you can land this in 3 months. Okay. So going back to our data collection. Is data accessible? That's the first question. Like, can we acquire it? Like, for example, let's say you need to use something personal information about healthcare industry. Obviously, that's going to be really, really difficult. I'm not saying impossible, but difficult. You need connections, you need people, doctors and stuff like that that's going to vouch for you and stuff like that. Who owns for copyrights? Are you going to own the copyrights when you acquire the data? Are you going to build the data pipeline or the project before actually jumping on the project, stuff like that? And obviously, if you're in Europe, you're going to care about GDPR a lot. And that actually creates a lot of barriers as well. People are not ready to go on project because of GDPR, because you need to take care of how, who, and stuff like that can look at data. So all these 3 questions are really, really important, and you need to take a good look at these questions before actually collecting data. Obviously, if you're just an engineer in this project, you don't really care, but people before you need to care about these questions. Do you have enough data? So obviously more data generally means better, not always, depending on the model, depending on many questions. Generally, more data is equal to better. But then like questions arises, how fast are we going to require data? For the project that I just mentioned, the offline deployment one, they need about 2 weeks to provide me with a couple of hundred more samples. So I need to work with limited amount of data every 2 weeks and actually try to improve the model every 2 weeks. So sprint and a half, depending on the length of a sprint, you're going to basically have additional data. So you need to revisit your approaches and stuff like that. And I did account for that in my project management stuff. So I have knowledge of like time-bound stuff about the data set. Obviously, the question is, should we hire third-party labeling team? That's always the question. So I actually trained one of labeling companies in Europe on this exact effort, and they actually increased the knowledge of machine learning as well as sales because they knew how to approach their customers who acquired more data. But like third-party labeling is always difficult because you need to dedicate one person who is going to communicate with them and manage them as well. yes, they have their own potential process and stuff like that, but generally, um, yeah. We'll have a data drift or data staleness. So that's a really important problem, question, and problem as well sometimes. What I mean by this is sometimes you can predict this. Like, let's say you are training, back to our COVID example, you're training your recommendation system on pattern of usages of your platform in the COVID time. You know that COVID is not going to last forever. Either we are going to adapt to it, or it's going to go away and we are going to go back to similar patterns of behavior. Not exactly the same. They will be still influenced by that. I mean, this means basically that you are ready to change the model in couple of months, couple of years, and that's fine. Like, if you have a knowledge, if you have information in your head about that, I'm completely okay with that. But yeah, so just to question that. And obviously data usability. So the first, like, sometimes your data, you have a data, but it's not useful. Like, we had a comment that most data is not labeled. Yeah, it's not, and most data is not useful. So usable. You have a lot of data, but that data cannot be used, like processed or whatever, because it does not provide any value. Like most logs, like most data that we are generating are logs. Like maybe 10% of logs are actually useful, but 90% of logs or even more is just like a fill in the gaps and stuff like that. Like for some cases, yeah, it might be useful, but generally logs are not structured well. Okay, we have two questions before we continue. Are all projects agile? Um, in most cases, yeah, I would say yeah. I love working in agile methodology way, and that's why I practice it. And generally, like whenever you work with multiple clients, as a consultant, as whatever, as an external like contributor, uh, if you pressure them to give you all the specification, they will give you more than required. I said it correctly the first time. And people will be in like a clutch and needless to provide more and more information to you because you're pressuring them. I don't like that. I'm staying. Let's say, what is the MVP? Let's build it, and if you need more and more stuff, we can add it. But let's keep it as simple as possible at the very beginning. And whenever you introduce machine learning, that's a completely different mind shift in a way of working, because that's something that's not guaranteed. That's something that you as machine learning engineer cannot guarantee that it's going to have that accuracy that you promised, because that's why I'm not promising any accuracy. Yes, they have a KPI of like being 80% correct. Amazing. You should have, but sometimes it's not feasible. You don't have enough data, you don't have good data, you have like many constraints that might go along a way, so you can find out while working on those projects really fast and iterate with them, correct KPIs, help them like set timelines according to that and stuff like that. So people, like machine learning projects are really dynamic ones, and you need to always educate your client, because clients are not really in machine learning space. That's why they called you. And one part of your job is to educate them. If you are internal contributor, like if they hired you, still you need to educate your business stakeholders, because they don't know. They are business stakeholders. They are amazing for what they do, but they have you as ML engineer because you are an ML engineer. So that's it. Is it difficult from a business communication standpoint to ask clients to label their data? It can be a time-consuming process for people who lack the necessary skills, and they may never will business label their data. I help them hire the team. Like for example, the example from before, founders, because that's a small startup. Founders need to set up the stage. they need to label a couple of samples themselves because they know what they want. They can explain to me, and I will understand my way because, as I said, I have my own biases, I have my own understanding and stuff like that. And that might not be aligned completely with them, and I don't want that. So I give them to label a couple of examples, and then we sit down and say, okay, cool. So let's see if you need a tool for this. Then they acquire a tool. I propose a couple of tools, and then they hire people. I help them with hiring process if they don't have a specific skill set for that, but generally they do. So I don't interfere into that. And then after they have those people that label the dataset according to their standards, I just come and basically do the project. And obviously I iterate and help with them, so people will constantly iterate and label data and process the data. And I know best practices for creating a labeling teams, like how to guarantee that your bias is the lowest one, even though you're hiring from the one country or from the one team, external, internal. I know how to organize the process, actually the best one, to check if they're okay and help them on board as fast as possible without needing like 10 weeks to onboard on labeling process. So basically there are techniques that I picked up along the way, so I can help my clients set up those processes for them as well. But generally, like I sit down with them and we like come up together with all those answers, and then they basically do the rest, and I do what I do best. That's it. Does it answer the question? Yeah. Okay. So generally, people ask me how much data is enough. I don't know. Nobody knows. There are metrics. I put them here. You can read them, but that's definitely not the right answer. Like you will, you can follow this like heuristics stuff like that, but then, as I said, they might be okay for some project, for some other might not be. Like the best way to look at these things is these are there similar projects that are done in the past that we know, like in research papers, in news and stuff like that, and we research them and say, okay, cool, these projects are done in this way. There is a data set, for example, public one that is really similar to something that you like to do. Here's how much they have. So you take those references, and that can be a good reference as like how much data generally was needed. But as I said, like every project is unique, every dataset is unique. Like one different image and your dataset is unique. And basically, that's where you need to like start experimenting, labeling more stuff, doing the best job that you can with the stuff that you have, and increasing the capacity of your dataset as the project goes on. It's rarely the case where I started with the same amount of data and ended up the project with the same amount of data. In the project, people will deliver you more data, more quality, more stuff like that, and you will need to adapt to that. As I said, I generally never had a project where I started with 10,000 samples and ended up the project with the same amount of data. Generally more. But yeah, as I said, you will have this slide. Here are just a couple of examples of how much like ballpark data you will need, but don't take this as a like rule of thumb. It's just a suggestion. Sometimes it will work, sometimes not. Cool. So problems with data collection. As we already discussed, it can be expensive. Let's say take an example of labeling dataset for self-driving cars. You have an image. You need a lot of labeling hours into one image. you have, let's say, at least 2 hours per image. You need to label all the cars, all stop signs, all lights, all roads, all marks on the roads and stuff like that. That's the first stage. Then you can do that from a couple of people. Like 2 people might do the same job without knowing. And if the third person can be a Q&A and test both and take the one with the best quality. So collectively, it will take about 1 hour and a half per image. And that can be expensive. Like if you are paying, let's say, $15 an hour for a data labeling person, that's about $45. Not 45, but okay, yeah, 45. Let's just circle it out across all labeling people to label only one image. So it's $40 to $45 per image. It can go more if you need more information from a single image, but generally that's how it can be even more expensive. Generating like a lot of random samples, not random, rare samples, where you need something physical to happen. Let's say landing a rocket. You can't generate, there are simulations obviously, but generally none of the simulation will be as good as the real deal. So real samples are going to be worth a lot more money. So obviously that's the case. Then we talked a lot about bias. There are a lot of biases. Sampling bias, basically a bias if you pay somebody to do something, or company that, let's say Coca-Cola, pays you to label the data set. Obviously you are going to prefer Coca-Cola subconsciously because they gave you a lot of money for that, stuff like that. Then there are obviously stereotypical biases, labeling biases, selection bias, like easily available data source and religion bias and stuff like that. There are a lot of biases, and obviously that might be the problem in the dataset as well. And their poor labels, dataset quality, and noise are something that generally happens as well. So, what we consider as a good standard for a dataset: complete information. So every single every single sample has exactly information that we need, like from the feature side to the labeling side. Then we have a balanced data set. So if you have 10 million samples of non-terrorists and only 600 of samples of terrorists, I would say that's a good data set because actually represents a real scenario in the real life. But that does not mean that's a good that's a good data set in the sense of statistics, because there is a lot more data for non-terrorists to terrorists. Okay. Then you have production representative samples. So what I mean by that, we talked about that a lot. So you want to have samples or data that actually will be used or will happen when you deploy the model. So if you talk about as simple as cats and dogs, you'd like to have cats in outside and outside, as well as dogs as well. So you need to think as a user, so you can actually recognize what's going to happen once they get hands on your product. Unbiased as much as possible. You will never have a data set that is completely unbiased. There will be some biases. Then you have consistent labels. So you basically sit down and decide with your labeling crew, hey, this is how we're going to label. Please don't label your own way. So it should be as objective as possible in the labeling sense. That's it. So feature engineering. Feature engineering is a creative process. It relies on you to basically create samples or inputs to your machine learning model. You are using raw data, processing it, like resizing images, transforming them, changing perspectives, changing colors, schemes, stuff like that, rotating them and stuff like that, to be able to create a good set of inputs to your model. And obviously, like, for example, for tabular data, we already talked about quadratic feature values. So we already done that, and we use that for our linear regression. But there is a bucketing. For example, if you have continuous values, let's say age, you can set, let's say, let's take 5 different subgroups of age from 1 to 100. So one group would be from 0 to 20, then from 21 to 40, then for 41 to 60, and so on. Okay, you got the gist. Then you combine different features. So let's say right now I have a project where I combine a couple of features to create a proportion of sizes between different samples and different items. So I can create correlation that does not exist actually in the data set. That can be done if you are able to replicate that in production as well. Okay. Then obviously there is a filling missing values. There is a lot of discussion on how to properly fill in the missing values, from interpolation to extrapolation to just mean, like using a mean value to removing completely samples. Like there is a lot different ideas on how to fill in the different the missing values. And obviously there is one hot encoding, which we already done as well. So whenever you have that dummy variables, get dummy variables, that's basically what hot encoding. Okay. Now we are going to go into different types of data that we didn't work with. We're going to work with, but now let's just discuss like some of ideas on how to work with that. If you don't understand some of these concepts, don't worry. We'll talk about them once we go and work with that data. So this is for text. So we have a bag of words. Bag of words is basically taking unique words and checking out how many types. Basically using that each word and assigning a random number to it. It can be an ID, it can be a random number, but it should be unique. Let's say I can be a 1, a love can be 2, car can be 514. And basically whenever you represent a sample, you'll, instead of words, use those IDs. Based on count, that can be done as well. So basically taking a number of words, unique ones, and checking out how many times they appear in the data set. So I can be is actually repeated a lot more than, for example, a car, and vice versa. And for example, the, a, and stuff like that, those like stop words are mostly repeated in the language as well. Then there is TF-IDF, term frequency inverse document frequency. So basically taking amount of time that word repeats versus how many times in how many documents, and they are basically that. A document can be a sample, can be actually a document. If you have, we talked about like a different, the use case of a lawyer company, not lawyer company, law company in general. But yeah, basically each document, real document, can be classified here as a document as well. N-grams, so basically representing each word. Okay, so basically each sample can be represented with n-grams. So let's say I love a car, or my car. Then if you have n-gram of 2, you're basically taking two words at a time. I love my car. Those will be n-grams of 2. And hashing trick, we'll talk about that later. And word vectors as most advanced one, which will be basically representing each word instead of IDs, like we did here, or certain like frequency. We're going to train a specific algorithm or use predefined weights for each of the word. And yeah, basically that's, for example, for text. Then for images, I gave a lot of examples with images, but generally, like, we talked about like tabular data where each of the columns we consider to be a feature. And we had the age, we had a name, we had a gender, we had whatever, In computer vision, each pixel of an image is considered to be a feature. So you're basically directly learning from the pixels. And whenever we talked about like feature engineering in this sense, we are applying certain transformation on images. So it can be like changing randomly channels. Like if you're having in color image, you're generally going to be RGB, red, green, blue. So you can transform it to be green, blue, red, and so on. Then you can basically flip image, so rotate it. You can change colors from RGB to grayscale or without color to HSV and stuff like that. We're going to talk about and do all of this in our computer vision week. Then we can add noise. So if you remembered, well, potentially you saw that somewhere in the internet. Basically, you have those CAPTCHA images that you need to compare, like, hey, where is the chimney, where are stairs, stuff like that. Sometimes there will be a CAPTCHA image, questionnaire where you will have like random dots on top of the image. Those random dots are represent a noise, potentially uniform or Gaussian noise, that are there to serve as a confusing parameter to computer vision models. So if you and I sit down and train a model to recognize where our chimneys are, and they can click automatically without us, and basically computer is using an algorithm to click. So a robot is actually saying, I'm not a robot. That sense. People from Google, from CAPTCHA, said, okay, we'll add noise to this image. It's going to be visible noise for humans. But if you have a chimney behind this noise, humans will be able to see it. But because you have this noise, and we said that features are pixels, that will confuse our machine learning algorithm, because suddenly we have crazy amount of like randomness because it's a noise in the image. And when we perform some calculations on top of that noise, it won't be visible for an algorithm. So what we do, basically, we need to find a way to either work around it or don't use machine learning here. Okay. And then we can basically add natural effects. So that's basically done really often in Tesla, for example, or Rivian, or whatever self-driving car company that you use. So you can add snow, you can add rain, you can add shadows, you can add noise intentionally, but to like reflect something, reflection of a I don't know, of a car, stuff like that. And then you can simulate basically what can happen in production. I've done that for a couple of clients. So one of my clients was a Dubai rental company where I had to train an algorithm to recognize chassis number. And in Dubai, there is a lot of sand. And most time, basically, when they take picture of that plate, it will have a like either dusty sense to it, or it will be a blurry one, because it's like in a really difficult place to take a picture of. There were a lot of images taken from glass, behind the glass, so there is a glare, there is a flashlight, and stuff like that. So I needed to replicate that into the data set before training the model. And what are good features? Well, so whenever you start working with features, it's not always the training part important, but always you need to take into account the prediction part as well. So let's say that the Dubai example that I just mentioned, whenever somebody take a picture of the chassis number, they immediately want to see it on screen, like maybe a second or max 2. But if you need to take 10 seconds to compute it, like somebody's sitting down or standing in like 50 degrees Celsius sun, that's really difficult, So you need to decrease that to 2 seconds. And whenever you start about the good features, there need to be easy and fast to compute, because you're going to do that constantly for users in production. Then they need to be always reproducible, so reliable, not stochastic. Like whenever you use randomness, you can't replicate it. So what I mean by that, like sometimes you need to add random noise to it, but use random state. So you can random state sample around that part of the random space, okay? And it should be low correlation with other features, so not to create multicollinearity problem or a problem that actually it learns from that generated, I don't know, feature that might not be reproducible and so on. And you are basically training the model on top of that, and once you put that in production, you're screwed. Okay. Be aware that sometimes there might be a data leak. So what I mean by that, like whenever you do a feature engineering, you need to make sure that there is like okay proportion of like unique images into validation and test set, and make sure that you don't have exactly same images in a training set as well as the test set and validation set. And overcome this, basically split that and apply feature engineering steps after that. So what I mean by that, let's say if you're computing mean of a column, don't compute a mean of a column of a whole data set, but split it into training part and testing part or validation part. Then compute that feature on top of training set and apply that to test set. Okay. So if let's say if a mean of a whole column of age, for example, is between let's say 54, and then you apply that to a data set, that 54 might contain information from validation set. But when you split it to training and validation part and take the mean, your mean might be lower. It might be 45. So that for that column, your mean is 45. That's what you trained your model on. That's what you do. Okay. That's important. So best practices, log everything. Every single step that you do, write it down. Write down what you changed, write down what results, good, bad, I don't care, write it down. Store model with extraction code. So every time you store the model together in one bundle, store your features as well. Feature extraction code as well. It can be like separate branches in the GitHub. It can be used as a separate project or branch of a project in weights and biases. It can be stored everything together in one checkpoint file. Whatever it works for you, or protobuf file, whatever works for you, that's fine. Just store it. Isolate each feature extraction code. So test everything, test often, test together, test like you should test everything as a unit test, with integration test, with production test. So use every type of test whenever building this type of project, and make sure that you isolate, as a sense, like every single part of your change or a pre-processing code should be a different one, like a function wise. If you are resizing the image, that function only resizes the image. Whenever starting a project, don't care about rules, go wild. Take a couple of weeks to explore everything that you can come up with. Brainstorm with your colleagues, brainstorm alone, with notes, with different projects on a GitHub. Try everything. Converge to something that you might work. Don't limit yourself immediately to use certain type of features. Later you can converge to that. When you start a project, go wild. So if you have a legacy system, that's fine. Like if old model, rule-based model, use that as an input to the new one. So you can do that. Because legacy models actually works, but not good enough, not decent enough. because like if it didn't work in the first place, it won't be legacy. So yes, it works, but it might not be broken. It might just not be on the criteria that you want to reach. And try not to use features that increase their value over time. So for example, number of kilometers run by your user. Like every time you run more kilometers, obviously you're going to increase that number, or number of kilometers that you have in a car that your car passed. So those features are bad. I wouldn't suggest using them. Okay, cool. So if you have any questions, shoot, or we are switching to model training. Okay. So about model training, decision before training, before you start with your training process, you should make sure that your data scheme is correct. Okay. Then define performance level. So what I mean by that, define baseline of your model. It can be your legacy system. It can be a human level. You can find similarity to some papers and use that as a current baseline. Whatever, or just basically use like a random sampler to find a baseline. That's it. But you need something to compare your statistics on. So have something prepared, have something as a baseline, and then work your way up. Then performance metrics. Consider with business, sit down with them, discuss with them, and see what actually works with your project, with your goal, and use that as a starting point. Then I talked about different baselines, but basically a different performance level. I meant here, what do you want to achieve? Do you want to achieve like 99%? Do you want to achieve human level performance? Like generally you would like to overcome the baseline, but generally that's the case. Then think about feature engineering and creating subsets for your data set. So for training, validation, and test part. So that's all to consider before training. Now, start with the selection process. So there are a couple of questions that you need to answer. And there are a lot actually, more than this, but generally. Do you need to have explainability built into your model? For example, when I worked with banks, they all need to have explainable decisions, like why they decline somebody. They need to know before even going to production. Then, should we use the incremental learning? Size of the dataset, prediction time, training time. So sometimes, like prediction time in Photomet, we were limited to 0.7 seconds on the round robin. So sending the request, making prediction, and returning the request. So you need to find a model that actually suits that. You can basically have a ChatGPT there, that big of a model, not ChatGPT as a model, but that size of a model. But ChatGPT requires like 25 seconds to make a prediction, full prediction generation. So obviously that's not feasible in that sense. Okay, so all these questions are important to answer, and obviously you're not going to see that and define that alone. You're going to potentially help with the team and with the business side as well. Okay, so training pipeline generally looks like this. For OCR, let's say, you take a dataset loader, so you load the dataset into memory, make augmentations. We call these augmentations here because it's image, but generally it's an image, but generally feature engineering. Then basically augmentations, image, and label pre-processing, all that done to the data. Train the model, save the mesh model, and select the metric, and test it on the select metrics. So that's basically how it works. So we talked about choosing a good metric. So the best case scenario, you will have the one metric to follow. There might be some business metrics, but you should always strive to find one that captures that one and performance of your model. So if you can ideally directly converge between, let's say, revenue and accuracy, that's amazing. That's rarely the case, but that would be ideal case scenario. So choose metric, like we talked all about these metrics here, but basically you would like to have one metric to follow that you're going to be following on and on optimizing your model. We talked about what happens when you choose a wrong metric, so let's skip that part. And we actually talked about a data terrorist case here, so we can skip that. But generally, that's what happened. Training cycle examples like this. So define a perfect metric, choose an initial algorithm to train. It's not going to be final one. Ideally, it will be, but I never ended up with the same algorithm that I started with. Then you define some initial hyperparameters. It can be like something from the paper that you read. It can be a random one. It can be the initial default one. Whatever you find to be a baseline or starting point for you, that's amazing. Go with that or previous experience, or then iterate from that. Train the model on a training set with choosing hyperparameters, validate in a validation set, save the model if it's better than the baseline, and iterate. So we keep iterating on a combination of different hyperparameters that we choose until we reach certain threshold that we are fine with releasing. And basically, we can stop comparing with a baseline once we reach it and start comparing with the next best thing that we got. Cool. So problems with models and their solutions. There are many. So they can be too much complex or too complex, too much regularization. We'll talk about these terms once we reach to deep learning. Too small data set, poor design of a data set, and so on. So basically all of this we actually talked about, but generally this is a slide where it put everything together. Best training practices is optimize for a business related metric. Think about production early. So try to go end to end. And somebody mentioned agile project way. So when I start thinking about a new project, I'll definitely think about what is the end goal. What is the whole pipeline going to look like? Like how I'm going to serve this model to my user. Is this going to be a API? Is it going to be just like a browser deployment, mobile deployment, and so on and so on. Whenever I have those answers or doubts, I go back and iterate to clear myself, clear my thoughts, and get some answers to it. And once I'm ready, I'm going to iterate on those questions and get the right answers. Basically, use libraries that already exist. There are production-grade libraries such as TensorFlow and PyTorch. In this course, we are going to use TensorFlow, but I'm going to explore the PyTorch as well if you like. Generally, we'll have code samples in both libraries, so you don't have to worry. They're pretty similar. Write tests often and explainable code to you and your teammates so you can go more fast and iterate fast. I would suggest leaving notebooks as fast as possible. So I love notebooks for prototyping, but that's basically the first 2-3 days. After that, I'm putting everything together in a set of a library which is going to be deployed. Try to reproduce everything. So if some parts of the content is not reproducible, that's bad. So strive for reproducibility and obviously go tiny steps, like iterate and integrate certain tiny steps to your project. Cool. Model evaluation. We talked about that a lot, so I will just skim it like fast. So we'll definitely choose where we are going to evaluate. Is it going to be online or offline or both? When we talk about that, I mean, is it going to be in real time when certain prediction was made? Are we going to iterate and then answer that question immediately? Or we are going to go offline and basically come up with certain predictions, let's say 100, 200 of them, and then basically, yeah, that's the model. So generally, that's basically explained here. So offline evaluation is the traditional one. We train the model, compare it with our targets, the result, basically that. I talked about the already deployed one. So basically what I mean by that is whenever model is in deployment, we collect some predictions, collect a couple of them, hundreds of them, and then basically evaluate them by hand, just to see how good performance of the model is doing. Online evaluation uses online data, so basically tests the business metric. So it can be churn, online time, click-through rate, overall satisfaction. It can be monitored in real time, and we can basically use our model performance to directly correlate with that. Ethical questions obviously are always there. So test for robustness of a model, test for fairness of a model. So does it make like any decisions or predictions that are not okay with your morals or something that your product or company is not supporting? Obviously biases and stuff like that. So that's a bit tricky to evaluate on, but try to see like subgroups of test set and see where it makes mistake. Does it make mistake on I don't know, pre-racial bias cases or like age group case, stuff like that. So try to see what are the mistakes, what mistakes are, and see like if you can find some pattern in those mistakes. And obviously you can compare multiple models, and that's basically really useful to do, and it should be done. It can be like A/B tests, it can be G-test, multi-arm bandit, which is a reinforcement learning one, but it can be basically define a metric only on a data set, whatever. It can be anything of these. Generally, you are going to end up with multiple models, and whenever you have a model in production, you're going to like have more data one moment, and you are going to train on more data, and ideally overachieve the new model. So you want to change it. So you're not going to immediately switch the model with a new one, but you want to test it, like either shadow deployment, or like canary deployment, A/B testing before, like many others. So there are many deployment strategies that you can do, but generally that's basically before actually putting new model in production. On that end, we'll switch to model deployment. So there are different deployment stuff and techniques. So I won't go into details on benefits and basically how everything works here. It's fine for you to read it through. And if you're interested in learning more about technical side of each of these things, we can go and cover that later. Popular deployment of strategies, I already told you. So single deployment, basically deploy it. Silent deployment is without telling people to deploy model. Canary deployment is like deploy on a certain percent of users, let's say 5, and whenever you need, like you see that new model works, you increase the percentage of deployments. And obviously multi-arm bandit, basically to check what is the best case scenario of the model and put more predictions to that model that actually produces better results. And here are some cases from an engineering standpoint to think about once you start deploying the model. So model should be easy to deploy, code base structure, and should be end-to-end tested, obviously, scalability, reliability of the model, speed of the round robin, how easy is to roll back to old version, should be rolled back to old version, and so on. So these are just couple of cases. Like, is it fully encrypted end to end? Like, what happens if the data, if inputs leaks, stuff like that. So those are the cases where what you need actually to think about once you start deploying the model to production. There are many things that can go wrong. I won't go into these right now because many of them actually we talked about, but you can read through and they're self-explanatory. But this is just a model of to think about once what can go wrong when you're evaluating risks and stuff like that. And finally, we have monitoring. So monitoring is obviously all about catching stuff that can go wrong early. So we talked about model drift, data drift, and domain drift, and so on earlier, and we won't cover them right now. But basically, here are some use cases useful to you to know what each of these cases can happen, like data drift, for example, and how to catch them early. So basically, data drift, and here are some additional theory about that. So I think it's too late now to go into that theory, but that conceptually, once we have a certain data set that you trained on, you see that inputs are a bit or completely different that you trained on. So you need to check yourself and ask what might go wrong. So here's just some cases that and the things like on temporal basis on I would say on a time scale, like how often or how fast can something happen. Monitoring, so obviously why we are basically using here to make sure that we can catch this and do some action regarding that change. So it can be either retrain the model, putting model on hold, making predictions, returning only 1, only 0, only null, whatever might be the case, just to make sure that you're okay with that. You're going to monitor a lot of things all the time, like metrics, user behavior, length of each processor in the production, like model extraction, model prediction, feature extraction, prediction scaling, stuff like that, batch predictions. Do consider batch predictions as well. Like all those are going to be monitored in the system logs and stuff like that to make sure that you can compare later on and improve your system. And obviously this is the last slide, just how to set alerts. So when you have to monitor something, you can always take a reference data and you say monitor for this case. This is a certain step that I expect to happen, like whenever, for example, distribution of data changes by that much, like a mean of certain column, please notify me so I can work around that and train a new model. So I know that I went a bit fast at the end because there are a lot of concepts that can be covered in a lot of detail, but we are already 2.5 hours in the session. I know that you're tired, so it's Friday, and yeah, so please shoot me messages, shoot me questions right now if you have any. But so you don't have to know all of these things. Most of these things are really easy to implement. There are a lot of tools to handle this. Generally, when you work on machine learning like projects, I didn't want to leave you with only like model side, but to tell you that there is much more. And whenever you read about machine learning, people will tell you about certain aspect of it, like data, machine learning, model itself, stuff like that. But after that, and questions actually around it are really important as well. And yeah, so do you have any questions? Oh yeah, yeah. I will definitely share with slides with you because there is a lot of stuff that you need to remember in the long run. So this will be serving as a like checklist for you to think about. Yeah, you're welcome. I hope this helped and provides just a bit of a glance of a like what is the complexity of a machine learning project and all the all the things that we need to think about once you start like from a simple project. Like there might be a simple project as the one that I mentioned a couple of times, but also like for those projects, um, yeah, there are many things to think about. Yeah. Uh, yeah. Thank you so much. Um, Thanks so much, guys, for being here. If I'm always there for questions. Have an amazing weekend, and there is no homework. Relax. Next week we will be tackling deep learning aspect of machine learning. Maybe we'll start a bit earlier. I will definitely let you know because I need to drive to another country just after our session, and this is already 8 p.m. for my time. So I'll definitely drive long into the night. So I'd like to start a bit earlier just to get get in okay time to that country. But yeah, so uh, thank you so much. There is no homework. Relax. If I'm always there if you have any questions, and yeah, so see you next week and Wednesday. Bye.